This is probably the first time I can see the RISC-V and ARM2 architectures can coexist in the same session. Thank you, VeTSS, for making that happen. So yeah, I'm Ashish, and I'm responsible for everything that goes wrong at Axiomise, and anything that happens cool is Sadeg's glory and my staff. And I'm going to talk about RISC-V in particular, but most of the stuff I'm talking about today is relevant for everything that we do, which is not RISC-V, and what the world does, which is also not RISC-V. So this is the semiconductor verification report card. I thought I'll bring this along because usually my talks are given in semiconductor conferences and verification conferences. People kind of get bored. But I think some of you may find it refreshing to know that actually, as an industry, we are not doing very well. So based on the Wilson Research Survey that Harry Foster compiles every 2 years, 76% of the IC ASIC designs are going through respin. If you're building anything in 2 nanometer nodes or 3 nanometer, you're talking about $25 to $30 million for a new thing to come back from TSMC. Projects are regularly running behind schedule, and even if you were doing FPGAs where people believe, okay, it's not an ASIC, so it's not coming back from the foundry, 84% of them are going through non-trivial bug escapes. And I've done PhD at Oxford, and I've done a lot of work with Hall theorem proving and model checking, had engaged with Intel in the PhD work. And when I came out, I was just ecstatic that, we'll conquer the world and change the world. And that was about 20 years ago. And I still feel we are literally just scratching the surface of how we can actually transform the habits in the industry so that this does not look as bad as it may seem. 62% of the logic functional flaws that are causing respins are in designs greater than 1 billion gates. That's a lot of hardware in this room, for example, would fit in that kind of a thing. So why is that happening? So based on the work that I have been doing at Axiomise and previously to Axiomise, my view is that we are actually lacking a holistic approach. So on one hand, Jar's talk was on architectural work based on the ARM, and ARM has been working on this for a very long time. A lot of the verification work that gets done in industry is usually at the microarchitecture level, and then people have been using formal in industry through RTL to netlist type equivalence checking, and then a lot of the hard work actually goes on in things that are called like gate level simulation and timing analysis. But actually nobody is thinking about the entire food chain and what exactly is going on when different bugs are being caught in different sets. So this overlay is not telling you that power is the biggest problem. These things have been laid out to show that there are overlapping concerns. So when I verified some of the earliest RISC-V cores, that was about 5 years ago, what I was finding is that sometimes power optimizations were causing security hassles, or they were causing chip to deadlock, or they can cause, X issues can cause lockstep to not work correctly. So over the years, I have presented different results in different conferences, including in RISC-V summits. But I just wanted to take the opportunity to remind us that actually this Venn diagram has not changed a lot, even if you're thinking of it outside the purview of RISC-V. So when we are working at Axiomise on customer projects where we are verifying silicon designs for other customers, I tell my team that this is exactly how the verification plan should look like. So when you're focusing on microarchitecture functional verification, even if the customers are not asking you to, be aware that these overlaps may exist. So it's important to understand that we need a more integrated way of thinking through this. And RISC-V kind of provided us with the opportunity to test the whole gamut from architecture to microarchitecture. So that's why I find this to be very interesting. So simulation, of course, in this room, I don't have to convince many people that simulation is probably not good enough and can't actually verify every case. But interleaved instruction sequences, do they work always as expected? Even for a small core, 32 registers, 60 plus user instructions, I mean, it's not easy to verify, for example, if data forwarding is implemented correctly in the RTL or not. And what's going to happen is if the cores get in order or out of order, and things get much more trickier with speculative branches and forward and backward jumps and back-to-back memory operations with all of these things with complex cache memory subsystems, I mean, there is no chance in the world that you can actually find a stimulus that is going to go and exercise all of the possible scenarios that are going to manifest as a design issue. So this is where a lot of the work we do for our customers becomes handy. Why these things are hard is because of this. So if you just take a step back and focus only on RISC-V, we have the unprivileged ISA, we have the privileged ISA, we have a very thriving sale specification. In my view, all of these three things are not as well as they could be because none of these three are fully executable, at least from my point of view in a formal test environment. I can't actually run any of these three things on an actual RTL to find bugs. Microarchitecture is needed because it provides the missing gap and tells me what optimizations have been implemented, what interfaces have been used, what interface specifications there are. This is also a specification. Well, actually not really, it's an implementation, but it is also a behavior that describes what the design does. And then there is us. So the properties or the model that I have created in Axiomise, let's say, what does that look like? So there are too many moving parts, and then you put all of this in a formal verification tool to ask the question whether this model always agrees with this. And that's what we have tried to do over the years, and I want to tell you what kind of results we are getting and what is working and what is not. So this is what the results look like over the last 5 years. Short summary, as I said, not enough time to capture all the details. What is very interesting is that when I verified IBEX and Zero RISC-V, a lot of people in the community said, oh, these are toy processors, they're only two-stage pipeline. The remarkable thing is that this chap was already in silicon when I found these bugs. This, fair enough, was under development in the very first week, and because this was a near clone of Zero RISC-V, I wasn't expecting to pick up anything in IBEX in the first week. But you could argue because designs are going through a change, you are going to find bugs, so that's not a big deal here. And with the CV32E 40P, this is a core open source. All of these are open source. This is a 4-stage pipeline. And this was being done by a big team of engineers, different industry players were involved. And this WAR5 was interesting because whereas these ones were previously verified by simulation, this was previously verified by formal. So it's not that formal is a panacea and that everything is going to be hunky-dory if formal has been used. Nice. So there were mistakes made by the other team that verified WAR5, and these are mistakes that most verification teams can make, which is, oh, I don't understand the spec, let's basically tighten up the implementation, make the implementation and the test bench the same. And this is why the previous team missed some of these bugs. But what is cool about finding these is that it took me no time to find these with the app that I built for this in the first version. So what I created originally, and now we have come a long way in the 4 or 5 year time frame, is that this particular solution is not only just doing architectural verification, it's also picking microarchitectural bugs, and is also coming fully powered with coverage analysis, which the industry considers it vital to understand why should any verification be trusted. So the way this works is we have the ISA, which then is being used by us through a manual process to translate this into system Verilog properties, which are basically then going through a setup phase whenever a new microarchitecture implementation comes in, when a new core comes in. And then the property set is sent to a formal tool. This could be from any of the main model checking companies, Cadence, Synopsys, Mentor Graphics, once been used to, now they're part of Mentor, even YOSYS. Any of these tools, if you use, you can use them to actually find the bugs or actually find the failures. So what is nice about this is that this is like the canonical architectural behavior which captures time-based semantics of all instructions in one place. And when you bring your particular implementation, so long as we map the architectural signals to the microarchitectural signals, or actually the architectural signals in the microarchitectural implementation, then from that point onwards, everything is completely push button. Push button to an extent that actually a 10-year-old can drive this app and wouldn't have to do a thing. It can actually create all of the debug traces for you automatically. Everything could be shipped completely. This is completely hands-off if you wanted to go down that route. I'm not encouraging you to do it that way. So there are no test cases to write now. For a formal audience, this seems like a very natural thing to do, but believe me, right now in the industry, so many people are actually missing bugs because they're still writing simulation test cases. There's no manual checker to write, and there's no verification code to be written unless you're building checks for custom instructions. So the reality is you just put in your core and a setup file and a coverage spec, which I won't be able to go into detail today, but there is a lot of information available. I'll be happy to tell you later. But the reality is that you will be able to exhaustively prove that all interleavings of all instructions implemented in the RISC-V instruction architecture has been or has not been implemented by the implementation. And the scenarios that we specify in the coverage spec can actually check that specific scenarios can also happen in addition to the arbitrary instruction interleavings that have been checked. So it has a very powerful time-saving capacity as well as the ROI that comes from proofs and coverage. So the way this was actually used on the CV32E40P core was that as the project was evolving, as the designs were changing, we were actually literally taking a checkout and going and changing the setup if this needs to be changed. And there are a proof button and there is a cover button. You go press it, you go, you can have a nice time, come back, and everything is done for you. You will see, you expect to see dashboards like this, or you will expect to see bugs. So what do we do about the coverage? So there are lots of dimensions of coverage. And it's again a complex topic for formal community itself in the industry, never mind simulation and formal. But basically there are 6 dimensions to this problem. We start collecting the essential processor coverage metrics, then we capture the assertion coverage that is coming out of how many properties are passing or failing. We then make sure that our constraints are not too tight because they can prevent legal stimulus from coming in. We make sure that the checkers have completeness, as in we have not missed certain cases from checking. We use tool-dependent coverage guarantees that come from the EDA tools. We also use hand-based mutation, where we actually go plant bugs in the design to check the robustness of the test bench. And then there is scenario coverage that we invented 3-4 years ago, where we provide a spreadsheet-based UI, which can then take your user-defined scenarios and automatically synthesize properties in the backend that could be exhaustively proven in the tool. So this is our way of generating guarantees. And as I said, there are more specific detailed videos available. So we have a very thriving YouTube channel. If you go to YouTube and look for Axiomise, there are over 70 videos, and a lot of them are on RISC-V, so you can follow up on details as well. And as I said, these results come out of any EDA vendor tool, so we are not particularly locked into any specific EDA vendor. We just don't really care that much as the results just come out and they tally correctly. So what kind of bugs are actually being caught? So this is a very interesting bug. This is a branch if equal to instruction. The semantics is that if the values in RS1 and RS2 registers are equal, then you basically update the program counter with the branch address. The problem you've got here is that you've got a debug getting initiated. And this debug's timing is quite interesting because it happens to arrive while this controller FSM is in the decode state. And if this happens, then hell breaks loose. And actually none of the instructions, not just BEQ, but none of the other instructions work correctly. What is peculiar is that if this debug arrived in the first fetch of the boot set mode, then this processor would work correctly. You would never cache this problem at all. It takes less than 3 seconds to catch a bug like this when you run this in a commercial tool like Jasper Gold from Cadence, which is what I happened, literally just put the water in the boil in the kettle and turned it on, and by the time the water finished boiling, all the properties had failed. If you consider the complexity of a bigger design and the timing of all of these different signals, it's almost impossible to capture them any other way. So this is just a blurb to describe the history of this and what was going on at the time. This was accepted as a genuine bug from the designers in the IBEX team. This is a very interesting bug. This is a memory subsystem issue. You might be able to relate to it because of the previous talk. So what's going on here is that this is a processor. It's got an MMU. It's basically doing loads and stores, which is what most processors end up doing most of the time. Reads and writes to the memory. They try to first look up it in the cache. If they can't find stuff in the cache, they usually get what is called a miss. The misses are usually tracked in a miss buffer, and then when the data comes back from the memory, then it gets populated back in the cache. So what's going on here is this. So we have a load word for a certain address A, and it basically gets looked up in the cache, and there is a miss. So as soon as it gets a miss, you obviously go to the memory, and the data is sent back to the memory, and it's also getting tracked in the miss buffer because it has had a miss. So the data is found in the memory. Now what happens is that some cycles later, you have a write or a store word of a different data, D2, to the same address. Now the thing is, this particular store is not a normal store, so this is a bypass. It could also be an atomic. When atomics or bypasses work, the way they work is they don't actually go through cache. They go directly update the memory. So the principles are that they must invalidate the cache line, and they should render the cache line state as invalid. What's happening here is that you had a load here, so the request has come to the memory. The store has reached the memory because it has bypassed the cache completely, and the responses have also been received at the processor end. But what's going on here is that later on, so you can see the memory has been updated, but later on, and the response has been sent back to the processor, when you have this load come in again, it should not actually see a valid entry sitting in the same address. If the processor didn't have a bug, it should say, okay, I've had a miss, I'm going to go read the data from the memory. And it should find D2, but instead what happens is, because the cache line invalidation logic is buggy, now there are hundreds of ways why it could have a bug here. I won't go into the specifics, but the details lie in the implementation. So let's say you have a boundary crossing between the core and the memory, and you have a FIFO that's got a FIFO type bug. You could have a counter, you could have a race condition, you could have another processor come in and stall you. So there are 100 ways of making it wrong, but the problem is this was the bug that was caught in the silicon. So this kind of a bug is, again, when I describe it in a talk like this, makes it very obvious and say, why would you miss it? But if you're not taking a formal approach where you're writing an end-to-end read after write check for all addresses, you're going to be actually missing this. So the problem is a simple one, but the reasons can be enormous. And when you're looking at a design with 100 million or 200 million flip-flops, and you've got 20 different finite state machines interacting with each other with that much concurrency, it can be very, very challenging to dream of stimulus-based approaches. So this was a major issue. But I keep saying, okay, it is good for exhaustive, but then what are the results then? So this is one of the dashboard view of the CV32E40P. We were able to exhaustively prove the whole core anywhere between 6 to 12 hours, depending on which tool, how many licenses, and so on. And if you compare this with the effort of running this in simulation, that it's not even going to be exhaustive, but you can't even come close, right? Of course, the onus on checking whether or not these checks are the right ones goes back to the coverage story that I mentioned. And even if you were doing an out-of-order execution, so this is ASICS, it's again an open source core, you can see that we're verifying it exhaustively in Cadence's Jasper Gold tool. So challenges and opportunities are there. The opportunities came because it's an open source architecture, RISC-V, so a lot of people can design their processors, which basically means you have over 100 vendors in the world building RISC-V designs. The only problem is that not all those 100 vendors have the experience of an ARM or an Intel or an AMD or an Apple or an NVIDIA, right? So they all have to build it and build it in a way that it always works correctly. So we identified that there are challenges for verification, and usually the big commercial houses, big ones build big teams of people. You will have 20 to 30 engineers trying to verify a big processor design. So to make it easier for every company in the world who's building RISC-V design, this is one of the ways of actually guaranteeing high quality. So bugs are a natural consequence of design, and ones that are caught late in the design cycle result in very expensive fixes and catastrophic failures. We have heard quite a few this year again because of security issues, even with the big names. So where we are coming at it is that formal methods should be used early in the design flow. This is what we are working with our customers to make sure that we can intervene those flows and get in early so that we can find most of the low-hanging fruit, also the corner case bugs, as soon as we can, and build as much as we can an exhaustive proof of bug absence, because that's what customers are asking us. They're throwing at us big designs and are saying, we're coming to you because we know that we're going to get it 100% exhaustively proven. We don't make such guarantees. I cannot tell you that I can do that every single time, but we can come fairly close. And the way we come close is by following a method, and there is a method to all this madness. So architectural validation, which has been going on since 70s, since 60s, since the first processors came out, that is all that verification was. In today's terms, I think it should use formal, not just for RISC-V, but for other architectures as well. And our solution can be used by anyone. As I said, architects, designers, verification engineers without any FV experience. And the nice thing is that you can find bugs and build proof of bug absence, as well as obtain coverage models that are interusable between different tools and between simulation and formal. So it covers all the axes of dependencies with each other. And use any tool you like. We are not promoting any specific vendor at all. So that's the mantra. I'm happy to take questions. I hope I've not overrun.
So much. Questions for Ashish? No? Okay, so I was actually going to ask several questions.
Sure.
One is that I am fascinated by how much formal stuff you're doing, and I must say, until I heard from Rajesh and Sadak, I wasn't familiar at all with the work they were doing, so that's a failure on our part. So if we wanted to learn more about all of this, has this been published somewhere, apart from your YouTube channel and all of that?
Yeah, so there are papers in RISC-V Summit. That's where we published our work. There is a white paper on this. White paper is a little old. The best place would be to go and look at the presentations on the YouTube channel, so that's where we publish all our results. We are struggling to find time to put papers for conferences, just because it takes a lot more time to prepare these papers today. But yeah.
So the next question I had was more of a technical one.
Yeah.
So of course the focus of the talk was RISC-V, and one convenient thing about RISC-V is that it's an open standard.
Yeah.
But in principle, there shouldn't really be a reason that these methods can only be applicable to RISC-V. I imagine you can use them for other architectures as well?
Yeah, and that's exactly what we're doing. Yeah. So 99% of our business is non-RISC-V. So most of the time we spend in trenches is verifying other designs. They could be networking designs, they could be GPUs. In fact, almost our entire business is right now verifying AI/ML designs.
Oh, wow.
And that's because that's where the growth is, and that's where the industry is going. And a lot of these things that I'm talking about here are inspired from the work that we are doing in the field. The challenge is that you have very limited time in industry. People, the competition between the semiconductor companies means they usually have a few months between them to beat the other one. So nobody has the time to go write the most beautiful crafty specification, never mind. I mean, if we got a Word document, we thank God that actually we got a specification. Most of the time, we write specifications. So we basically talk to the designers. We have a way of doing it. And that's where things get a little bit more interesting, especially coming from when I started into this as a PhD. This is where fun is, yeah.
These big companies, do they usually allow you to talk publicly about the air bugs that you find in their designs?
No, they don't. So that's why I only talk about the open source ones. That's why open source is good. No, we can't always. I mean, some of the bugs we have seen and what we have heard the architects say is that things like, not in a million years would we have ever been able to find one stimulus that would have found this bug. And these bugs are usually caught in minutes sometimes, not even hours or weeks. So just one minor point I wanted to make here, which I didn't capture in the talk. A lot of the time people say, we are trying bug hunting, we are trying RTL, this, that. We are doing program reasoning. In software, you're verifying a C program or a Java program. We're verifying Verilog in VHDL or in some cases System C. It's not that different. The tools may be a little different. The underlying technology is still the same. So if you come at it from a program reasoning point of view, things get a lot more clearer and uncluttered. At least that's the way we look at it anyways.
Okay, thank you. I think there's also a question in the back, please.
Yeah.
Yeah. Hi, thanks for the talk. You mentioned in one of your final slides security. What do you do in verifying security issues like those speculative execution issues and all those things?
Sorry, can you be a little bit louder? Security, I heard that you're asking me something about security, yeah? What are we doing about it?
Microphone, please.
Yeah, I'm not sure. I think it only speaks over here.
No, it is working. Just
okay,
very
cool.
close. Yes.
So I'm just wondering what you can prove with the tools that you're using about security at the microarchitectural level.
Yeah, so if you look at the security, the way we are looking at it is the confidentiality, integrity, availability problem. So we're breaking it down into those three umbrella points and saying, look, if you can actually deadlock a particular area of the chip because you're basically denying the instruction or any other transaction the chance to make a certain thing available, then there's an availability thing. So we worked on categorizing these vulnerabilities based on the CVE, so vulnerability score mechanism. So this is very popular in software side, but in the hardware world, people are not looking at it. So we basically came up with formulas that people are using in software, and based on the outcome in the formal tool, on the checks that we have, we can come up with a vulnerability assignment. I didn't talk about it today in the talk again because of time, but there's also a talk in DAC I gave 2021, which is on what we are doing with security. It's a very big, security means a lot of things. We had a wonderful talk this morning from Strathclyde University that was also very insightful. So manifestations of security keys being leaked around, or can you actually have a Trojan that can actually manipulate the design so that it can read things that you don't understand. The cool thing about formal is not that it is making us think about what ought to happen. It automatically brings the dimensions of what not to happen because of the infinite stimulus. So because of that, if you are clear about your goals in terms of what security aspects you're going to be verifying, you can pick them up quite quickly. So I think where we are very good at is when proofs struggle, we know how to get them to converge. So if you start well with the right questions, then we can go a lot further. This is where a lot of the magic is. But yeah, it's a big field. I'm not saying we can cover a lot of the ground in this, but we're doing well. We're making a good start in that.
Thanks.
Thank you so much. Let's thank Ashish again.
Thank you. Thank you.